Okay, so chapter 4, 3 major classes of chemical reactions. Again, I'm just going to boil it down to the most important bits of what you need to know, but we're going to look at a lot of reactions in solution in this chapter. And what kind of solutions do we make in general chemistry? Well, usually we make solutions where we use water as a solvent. And so it says here a solution consists of a smaller quantity of one substance, which we call the solute. And so you should know what a solute is, which is dissolved in a larger quantity of another, which is called the solvent. Now, in what we call an aqueous solution, water serves as the solvent, and we abbreviate an aqueous solution as AQ. Say, for example, maybe I can fix up my letter Q there, AQ. So if we write sodium chloride solid, that means that we have, solid crystals, the white crystal in solid sodium chloride. If I write sodium chloride AQ, what does that mean? That means I have a solution of salt or sodium chloride in water. So this is an aqueous solution. I'll abbreviate it like that. Okay. Now, sort of a common thing that we do in chemistry is that even if water is present in a smaller amount, okay, we still call water the solvent. So anytime we use water, we have something dissolved in water, we always consider water the solvent. But again, these definitions for solute and solvent still stand. It says here that some solvents passively disperse the substances into individual molecules, but water is much more active, interacting. Water interacts strongly with the substances and even reacting with them in some cases. Now, a case of water reacting with something would be, for example, if you put sodium metal in water, you probably know that causes a fire, right? It causes an explosion. But let's talk about the nature of water and explain how and why water is much more active, why it can interact with substances, okay? All right. And in fact, where I did my undergraduate, my first and second and third and fourth year university, there was a professor in the chemistry department there that all he studied was water, okay? He was a very exciting person, okay? All he studied was water. So water is a really interesting solvent. It says here, the electron distribution in molecules of H2 and H2O. So let me just kind of walk you through what's going on here in this slide. If I have two atoms of hydrogen bound together, I get hydrogen gas, which is, where's my pencil? Here it is, which is H2, okay? And that's what's being shown here. Now remember, both of the atoms, hydrogen and hydrogen, those are identical. And so the electron distribution in the molecule is going to be symmetrical. You see how everything is symmetrical here. Okay. Well, what about if I have water? In water, if I draw a structure representing water, and you probably have seen water written in this bent shape before where there's kind of an angle down here. There's a reason why we do that, and I'll explain that later. But my point is this, is what makes water so unique, or one of the things that makes water unique, and these are all different representations of water here, is that the atoms hydrogen and oxygen have a different amounts of tendency to pull electrons towards themselves. What does that mean? It means that in a molecule of water, you have the nuclei, right? The nuclei of the two hydrogens and the oxygens, okay? Those are represented by these little black dots here, okay? Now, everything else is the electron cloud. And I can tell you that oxygen is more what we call electronegative than a hydrogen. What does the electronegative mean? It means that oxygen has a real tendency to pull electrons towards itself. So you see this delta minus up here? That means that the oxygen, and that's what's being shown here, H, and here's the oxygen, okay? The oxygen pulls more of the electron density towards itself. It's not an anion, but the delta means partial, partially or partial, okay? So it means the oxygen is partially negative, and what's that going to do? It's going to render the two hydrogens partially positive. We call that a dipole, and we represent it with this SATSI arrow here with the cross at the end. We put the cross at the end that's partially positive, and we draw the head of the arrow towards the end that's partially negative, okay? So that means that there's a dipole in water. Now, what you need to know is that the oxygen is partially negative and the two hydrogens are partially positive. Okay, so partially positive. All right, that's what you need to know moving forward. Now, what is that? What's so great about that? You're like, okay, Mr. Dion, you have a water molecule. Part of it's kind of negative and part of it's kind of positive. What's so great about that? Well, let me show you. There's something really great about that. Here we have a representation of what happens when you take an ionic compound. So this is an ionic solid here, ionic solid shown by these brown and beige spheres. So we have the cations and the anions. Now look at this. Here's the water molecule, okay? Overall, on the oxygen, you have a partial negative charge, right? Overall, by the end that has the two hydrogens, it's got a partial positive charge. What that means is that water can actually orient itself. Okay, so here's the anion. Look at the water molecules. Did you notice that they're all pointing in the same direction? Right? The negative end of the molecule is pointing away from the negative charge. And what's lining up towards the negative charge? The positive. Right? So what that does is, what does it do? It's going to stabilize it. Okay? And look at this. You see how all the water molecules here, you see how they're pointing in that direction? Now look over here with the cation. They're all pointing in the opposite direction. They're pointing towards it. Why? Because the partial negative charge, right, this part is going to point towards the cation, and what's it going to do? Opposites attract, and it stabilizes it. And that is why, and you're like, man, this ionic solid, it's so beautiful. Look how the cations and anions, how they all pack together. Well, the ions are going to be even more stable when they're in solution, and sometimes we call that being solvated by the solvent. Give me a thumbs up if you follow me on water. It's got kind of a positive and a negative, and it can stabilize a cation and an anion. Anybody follow me? Okay, great. Okay, I had to scroll down in my chat. I was like, what? I figured you would follow me on that. Okay. Now, what else can water do? Well, water can dissolve ionic compounds. Let me back up and just remind you that what we're talking about here is that water is dissolving an ionic solid. What's an ionic solid made from? It's made from a cation and an anion, right? Positive and negative. Okay, with that in mind, let's look at the next slide. It says here, electrical conductivity of ionic solutions. This is some kind of, light bulb with two electrodes, shown right here. And the electrodes are placed in water. So this is just pure deionized water down here. I'm going to move so you can't see the title. But anyhow, it says here, not deionized, it's distilled water. And they put the electrodes in there. Okay, then they plug the light bulb in, and the light bulb does not light up. Okay, there's no light. The reason why is because there's no ions in solution. Okay, when we have pure water, there's no ions in there. There's no ions. Okay, water is a covalent compound. It's made of hydrogen and oxygen, which are both nonmetals. Now, what would happen if you were to take those electrodes and put them in this is just table salt that's in here. Pretty cheap experiment, right? Okay, it says here, okay, there are positive and negative ions, but they're fixed in a solid and they cannot move. Okay, and they do not allow the conduction of electricity. However, if you make a solution of sodium chloride in water, right? What are we talking about right now? Solutions. If we make a solution of our ionic solid, what do we get? We get ions. We get positive cations and negative anions. And when you have ions, okay, in the solution, they are free to move. And what that allows it to do is it allows it to conduct electricity. Okay, and when a solution can conduct electricity, we call it an electrolyte. Okay, so we would call that solution an electrolytic solution, but we'll just say electrolyte. Okay, and when something can't conduct electricity, we call that a non-electrolyte. So remember, it's important that you understand that sodium chloride, the solid, is not an electrolyte, but when you put the sodium chloride in solution, it becomes an electrolyte because the ions, what? They are free to move. Okay, so what do we got? We need to have ions in solution in order for electrons to move, and you got to have movement of electrons if you want electricity. Important notes on dissociation of soluble ionic compounds. Now, every ionic compound that we've ever named, sodium chloride, potassium iodide, calcium bromide, whatever, they always have the same generic formula, right? We always start with the cation, okay? Then we put the anion, right? Suffix has ide, I-D-E. So we have well, not I'd for all of them, but anyhow, for a lot of them. Anyhow, so let's say here, it says, once you have identified the cation in an ionic compound, the rest of the formula is the anion. Now, again, you've already covered nomenclature. So you should know how to name any one of these 5 ionic compounds here. Potassium dichromate, magnesium chloride, ammonium permanganate, sodium chromate, rubidium perchlorate. You should be able to name all of these. You should be able to identify the ions. Let's take a look at this one here, potassium dichromate, in dirty detail. Now, potassium is element number 19 in the periodic table. It is an alkali metal, is what we call that group. And all alkali metals, all metals in group 1A, they all have a charge of +1. And that's why we know it's K plus 1. It's not K plus 2. Not +3, it's not +4, it's K plus, and it's always that charge. Okay, look at the next one, which is MgCl2, magnesium chloride. The same thing applies. Magnesium is in group 2A. It's element number 12 on the periodic table. It's going to have a charge of 2+. Okay, now let's go back to our potassium dichromate. We have 2 potassiums, right? 2 potassiums, and then we have 1 dichromate. And if you're like, whoa, how do I know that Cr2O7 is 2-? You know, how do I know that? How do I know it's called dichromate? How do you know that? I'll give you a clue. It starts with M, ends with memorize. The only way to know polyatomic ions is to memorize them. Okay? So this is something that we see all the time. And if you're wondering, you know, like, hey, Mr. Dion, didn't we already cover nomenclature? What the heck's the point of this slide? The point of this slide is that you've got to be able to look, you've got to be able to look at any ionic compound like these 5 that are listed here and say, okay, here's my cation, here's my anion. I know what the charges are, right? Because in order for you to understand ionic solutions, you've got to understand ionic compounds. Okay, with that in mind, let's take a look at a question. It says here, using molecular scenes to depict an ionic compound in aqueous solution. All right, we have a problem. The beakers shown below contain aqueous solutions of the strong electrolyte. What does that tell tell us if it's a strong electrolyte? It's going to dissociate into ions. So dissociates into ions. I'll even write that in capital letters. Potassium sulfate. Could you write out the formula for potassium sulfate? I hope so. Potassium sulfate, right? Sulfate is SO4 2-. How did I know that? I memorized it. Potassium, like we just said earlier, is always K+. Well, how many potassiums do I need to combine with my SO4? This has a charge of +1. This is a charge of 2-. So it must be K2SO4. Okay, I've got that down. Now the question is, which beaker best represents the compound in solution? Now we're not showing the water molecules. Could anybody tell me? I'll just throw that out to my wonderful students who've probably read the whole chapter, did the Learn Smart, tried some problems already. Who could tell me which one of these? Yeah, I'm going to have to go with C on this one, okay? Because remember, it says, which one of these beakers best represents the compound what? In solution, right? What's going to happen when we put a strong electrolyte in solution? It's going to dissociate into its ions. And so in beaker A, the problem with A is that you have all of the ionic compounds intact. The reason that C is the correct answer is because it shows the dissociation of the ions. What's going to happen is your K2SO4, right? When you put that in water, it's going to break apart into 2 K+ ions, right? Because there's 2 of those, 2 potassiums, and we already went over why the charge is +1, and I'm going to end up with a sulfate. So that means the ratio of potassium ions to sulfate is 2 to 1. Well, let's look. In beaker C, I have 1, 2, 3, 4, 5, 6 cations, and I have 1, 2, 3. If I have 6 to 3, that's the same thing, right? 6 to 3 is the same thing as 2 to 1. Okay? Give me a thumbs up if you follow me on that one. The dissociation of an ionic compound into its ions. All right, well, with that in mind, let's take a look at the next question, and I'm going to move to the next slide to help us out. It says, if each particle represents 0.10 moles, what's the total number of particles in solution? Okay, so we have a total of, what did we say? Here we've got three sulfates, okay, and we've got 6 potassium, right? All right, let me show you here. So it says, we already figured out that the formula for potassium sulfate, and I'm just rehashing this, potassium sulfate is K2SO4. When we take that solid compound and we put it in water, I just like to write H2O over the arrow just to kind of mentally remind myself of what the heck I'm doing. Okay, I've got 2 potassium, so I'm going to put 2K plus, and those are going to be in solution. And I'm going to have, I only have 1 sulfate, so I'm just going to write SO4 2 minus. Aqueous, like that. Okay, so let's think. If each one of these represents, what was the question? Count the number of particles in the relevant beaker, multiply by 0.1. Oh, I see. Okay, I see. Okay, so in our beaker, I'm gonna have to copy this because my memory is so short. Let's see, try this. Copy. Watch this. Okay. And I'll just paste it over here so I don't forget. There we go. So this was what was in our beaker. We had 3 sulfates and 6 potassiums. Okay. So if I have 3 sulfates and 6 potassiums, this is A. Oops. This is A. Then in B, for my sulfates, I'm going to have 3 times 0.1 moles. Right. So this is for my sulfates. There's 3 of them. I'm going to put 0.3 moles. And then for my potassiums, I have 6 times 0.1 moles. So I'm going to have 0.6 moles. Okay. I add those all together and I get 0.9 moles. Okay. Like that. Now it's asking me count the number of separate particles. So if I have a total of 0.9 moles of particles, okay, particles, what am I going to have to do? I'm going to have to multiply those by Avogadro's number. And if you're like, well, why would you do that? Because I know that I have 0.9 moles of particles, and I'm going to multiply that by, there are 6.0233 particles in 1 mole of particles, like that. And then you can see that moles of particles cancel out. We end up with the number of particles. I've already done the math here. You end up with 5.420 times 10 to the 23 particles. You might be wondering, why do I have 4 significant figures here when I only have 1 significant figure here? I guess in the solutions, you just assumed that that was an exact number. All right. There we go. So here's the solution all worked out. If you have your microphone on, if you could mute it, that would be great. Okay. All right. Let's see here. Okay. Well, let's take a look at another example here. It says here, let's see, do I have room to solve this? Yes. Okay, good. In problem A, says, how many moles of each ion is in each solution? Okay, let's take a deep breath. What this question is asking us, A, B, and C, is the same thing for each one of them. How many moles of each ion is in each solution? How are we going to know what ions we have? You have to be able to write out the name or write out the formula of the compound. It says if you have 5 moles of ammonium sulfate dissolved in water, what's ammonium sulfate? Right? How would I know what ammonium sulfate is? You have to be able to say, okay, I know that ammonium is NH4 plus, and I know that sulfate is SO4 2 minus. So the formula must be NH4, I need 2 of those, and sulfate, right? You've got to be able to come up with it that fast. Now let's look what would happen if I took solid ammonium sulfate, which is an ionic compound. It's made out of a cation and an anion, so it's ionic. If I put that in water, I'm going to break it apart into ions. So I'm going to end up with an aqueous solution of ammonium ions and an aqueous solution of sulfate ions. Okay, good enough. Now remember, we have 2 ammoniums for every 1 sulfate. So there we go. Now, what was our question asking? Our question was asking us how many moles of each ion is in solution, and we're starting it with 5.0 moles of ammonium sulfate. So I'm going to write that down. We're starting it with 5.0 moles of ammonium sulfate. Now let's think about it. Could anybody answer this by doing mental math? Could anybody tell me how many moles of ammonium ions you would have when you dissolve 5 moles of ammonium sulfate? How many moles of ammonium ions would you have?
Is it 10?
It's absolutely correct, right? We're going to have 10, right? And if you're unsure about that, think about it. The ratio here is 1. Get out the red pen. The ratio is 1. For every 1 of these, I form 2 of these. So if I start with 5, then my answer is going to be, I'm going to have double the amount. I'm going to have 10 moles, 10.0 moles of ammonium ions. Okay, I'm adding sig figs here, aren't I? Okay, I'm going to end up with 10 moles of ammonium ions. Same rationale. Could anybody tell me how many moles of sulfate ions I'm going to end up with?
5.
Exactly, right? Because the ratio is 1 to 1. Okay, so I'm going to end up with 5.0 moles. Now, if you need help on this, if you're like, oh, I'm unsure, watch carefully. Look, if we start with 1 mole, okay, because we have 1 to 2 to 1, okay, those are our coefficients. If I start it with 1 mole of ammonium sulfate, okay, from my from getting ahead of myself. If I start it with 5 moles of ammonium sulfate, from my balanced equation, I know that when I have 1 mole of ammonium sulfate, I have 2 moles of ammonium ions. Looky, looky. Moles of ammonium sulfate cancel out. 5 times 2 equals 10 moles of ammonium. No, 10 moles of ammonium ions. Okay, we do the exact same exercise for the second one. I start out with 5 moles of ammonium sulfate. I multiply that by a conversion factor of 1 to 1. And I have that solved over here. And so you can see that you form 10 and 5 moles of ammonium ions and sulfate ions, respectively. Give me a thumbs up if you follow me thus far. Ionic compounds dissociate into aqueous ions. You have to understand that ionic compounds are made of cations and anions. Yes, no, toaster? All right. Some of this can be done by mental math, and I'm sure some of you are, or most of you are probably all faster than me at mental math, but let's take a look at the next one. It says in B, I have to back up here to read the question. You start with 78.5 grams of cesium bromide, okay? So if we start out with 78.5 grams of cesium bromide, my 5 is kind of ugly, let me fix it. 78.5 grams of sodium bromide, okay? How many moles of cesium ions are we going to end up with? And how many moles of bromide ions are we going to end up with, right? That's what we're trying to figure out. So moles of cesium ions and moles of bromide ions. I'm just going to do the cesium by dimensional analysis, and then I'll show you that since the ratio here is 1 to 1, we're going to have both of them solved. Now, I'm going to put here 78.5 grams of my cesium bromide. I'm going to go look up the molar mass of cesium bromide, and I've already done that. In 1 mole of CSBr, that's not good. Cesium bromide, I have 212.8 grams of cesium bromide. Okay, I can see that mass units cancel out. Now, I'm going to use my conversion factor. I'm sure that some of you just do this like a back of a napkin calculation. If you get the right answer, that's cool, but make sure you're careful. There we go. Where did I get this conversion factor? Right here from starts with B, ends with balanced equation. It's the balanced equation. So you can see that moles of cesium bromide cancel out, and I end up with, and I've already done the math here, you end up with 0.369 moles of CS plus ions. Who could tell me how many moles of bromide ions would I have? Not a trick question. Mr. Dion does not like trick questions. In fact, I hate them. Who could tell me how many moles of bromide ions I would have? Thanks, Rebecca. Exactly. Liv says, good. Brianna, all correct. Okay. Since the ratio here is 1 to 1, that means I'm also going to have 0.369 moles of bromide ions. Okay. Just a little bit of stoichiometry. If you're wondering, it's 9:55, I'm tired. What the heck are you talking about, Mr. Dion? All I'm talking about is ionic compounds dissociate, okay, into their ions in solution. You got to know what a cation is and an anion is, and then we looked at a little bit of stoichiometry. Okay, there's the rest of the solution. I'm going to leave number C, and let's talk about concentration of solutions and molarity. So it says here that many reactions occur in solution. Now, most of the solutions that we're going to look at in Gen Chem 1 and in Gen Chem 2 are going to be in water. They'll usually be in water. If you take organic chemistry with me, you'll see that we do lots of reactions in organic chemistry. In fact, most reactions are not done in water. It says a solution consists of one or more solutes dissolved in a solvent. I'll tell you the good news. Most of the time in this class, not all the time, I shouldn't say, but a lot of the time we'll look at one solute, maybe two. Very rarely do we look at three. The concentration of a solution is given by the quantity of solute present in a given quantity of solution. And the way that we measure concentration, and if you're like, what's concentration? Hey, we've all used concentration in our everyday life, right? If you're making some Kool-Aid at home, you just dump in a little bit of crystals, you go, this tastes like dirty water, right? This doesn't have a good, delicious Kool-Aid taste, right? It's not, the concentration isn't strong enough. Then you dump in a whole bucket of, Kool-Aid crystals and you stir it around, you're like, man, this would rot your teeth, this is too concentrated. So these are things we're used to. And molarity, which we use big M like this, is often used to express concentration. So molarity, and you have to have this memorized, is defined as moles of solute divided by liters of solution. Okay? And what's so great about this is we have another way to calculate moles, right? And if you're like, well, how would I do that? All you'd have to do is rearrange this formula. If you want the moles of solute, okay, you would just multiply molarity times the volume, right, in liters. So molarity times volume. Now, moles of solute, I like to abbreviate that N for the number of moles. So N is M times V, like that, okay? And if you're like, what are you talking about, Mr. Dion? It's just number of moles, little n, is equal to molarity, concentration, times volume. And if you're not entirely sure about that, don't worry. We're going to look at plenty of examples of that. And this is going to be important later on when I show you a formula that you're really going to like for dilution problems. All right, with that in mind, let's take a look at a problem. Not meant to be a mental, breakdown or anything like that, just a plain old concentration problem. It says, calculating the molarity of a solution. What's the molarity of an aqueous solution that contains 53.7 grams of glycine? And they've given you the molecular formula here. Why can't they just give us a molar mass and make our lives easy? I don't know. Anyhow, molarity is the number of moles of solute per solution. So let's write out our formula. Molarity equals the big M, which is going to equal to the number of moles divided by the volume in liters. The good news is we already have the volume, right? Can you convert 495 milliliters into liters in your head? Did anybody tell me how many liters there are in 495 milliliters? Again, not a trick question.
0.495.
Yeah, 0.495. You just divide by 1,000, right? I've shown you the dimensional analysis here, so we can put 0.495 in our denominator. But where are we going to get the number of moles? Ooh, where are we going to get that? Can anybody help me out? Just give me a strategy. What should I do? I'm panicking. I'll take anything, any kind of idea. Amanda just typed out molar mass. Amanda, that was enough of a push to put me in the right direction. Yeah, she's saying, well, you have the mass of glycine, which is 53.7 grams of glycine. Glycine, by the way, is the simplest amino acid of the natural amino acids. Anyhow, now you have to go and look up the molar mass of glycine. Did I do it? I think I did. Molar mass of glycine is 75.07. 75.07 grams per mole. Here we go. So glycine And we know that in 1 mole of glycine, we have 75.07 grams of glycine. Well, looky, it's not magic. Punch that spinach into your calculator, and you end up with 0.715 moles of glycine. Now we can take that, put it into our, there we go, and looky, now we've got moles per liter. We punch all that beautiful spinach into our calculator like that, and what do we get? Moles per liter. Okay, let's see, when I did that, I ended up with 1.44 moles per liter. I can also report that as 1.44 big M, which stands for molar. All right, give me a thumbs up if you think you can solve this one. All you have to do is know that new formula. Cha-cha-cha-cha. All right, is it 10 o'clock already? Man, we should have an extended class, you know? Have it last until noon and just do a bunch of fun chemistry stuff together. All right, let's take a look at this slide here. And mass, mole, number. That's a funny, is there enough hyphens in this title? Mass, mole, number, volume, relationships in solution. Look, if you go, look at any general chemistry textbook under the sun, I don't care who wrote it, they've always got some kind of version of this exact, figure here, okay? And you're like, well, why is it in every book? Must be important, Mr. Dion, and you're absolutely right, okay? It's just trying to get you to understand, that you can't do things. You can't go from mass to volume directly, right? You can't do stuff like that. You've always got to go through what? Molar quantity, okay? So if you have the amount of moles, you can use molarity to solve for volume. If you have the number of moles, you can use molar mass to solve for mass. If you have the number of moles and you know Avogadro's number, which never changes, you can figure out the number of entities, whether it's ions, molecules, tennis shoes, whatever, okay? Doesn't matter, okay? Yeah, it's one of those things I can sit here and ramble on for a while, but it's just, the point is that you can always use the mole to relate between number of entities, mass, volume, and we've done this. If you're like, I'm not even sure what this slide's for, Mr. Dion, what do these arrows mean? Look, if you understood the problems that we just did, you understand this slide, okay? All right. With that in mind, who enjoys doing practice problems in class? It might just be me, but anyhow, I like practicing. Let's see here. Yeah, Violet says, I do in capital. Okay, I got a few me's. Good. All right, great. All right, so few people like to practice. I really enjoy practice. It's something I find very relaxing. You're sitting at home, get some scratch paper out, a calculator, pencil. Just try some fun chemistry problems. Let's see here. Problem. How many grams of solute are in 1.75 liters of a 0.460 molar sodium hydrogen phosphate? So I should say, okay. How many grams of solute are in 1.75 liters of 0.460 molar sodium hydrogen phosphate? Okay, I didn't read it exactly right. Anyhow, what are we going to use? We're going to use our good old formula that molarity, right, is equal to the number of moles divided by the volume in liters. You can also write that like this. Like sometimes I like to write it like this, N over V, right? Little n is equal to number of moles, okay? V, you can guess that one, is volume, okay? And big M is molarity. Molarity, if you can read my writing, anyhow. So that's all we need. And what are we going to be solving for? How many grams of solute? Well, for that, we're going to need the number of moles. Because once we get the number of moles, as one of my students just told me, she said, as long as you have the number of moles and a molar mass, hey, the mass, you can figure that out. So let's start with what we've been given here. We've got 1.75 liters. Let's start with that. Got a blank page. We got 1.75 liters of, I'm not going to write out sodium hydrogen phosphate because I'll just put of solution. Shoot. Here I am telling lies. Let me write it out. Sodium hydrogen phosphate. Okay, the concentration was what? 0.460 moles of sodium hydrogen phosphate. in 1 liter of sodium hydrogen phosphate. If you're like, how did you know it was 1 liter? That's the definition of molar, right? M is moles per 1 liter, right? That's implied that it's 1 liter. Okay, look, so now my volume of sodium hydrogen phosphate cancels out. Now I've got moles. Where am I going to go to figure out the number of grams? I'm going to go to my molar mass, which was given to me on the previous slide. And I know that in 1 mole of sodium hydrogen phosphate, I've got, 141.96 grams of sodium hydrogen phosphate. You know what? I think I have the answer in my slides. I don't know. Where's my calculator? So get out the old beast here. My calculator, 1.75 on 0.46 times 141.96. And that gives me 114.2778. Okay. How many sig figs should there be in my final answer? I've got 140. That's way too many. 2, 7, 7, 8. Can anybody tell me? 3. Joel says 3. Kenner says, somebody else says 3. Okay. So the answer is it should have 3 sig figs, right? Because we have 3. I'll show you why. We have 3 sig figs in our volume. Okay, we had 3 sig figs in our molarity, and then we had 5 sig figs in our molar mass. So we're going to go with 3 sig figs, right? And so this would round to 114 grams of sodium hydrogen phosphate. All right. What do you think? Could you do that one? Give me a thumbs up if you think you could nail that to the wall. Say, I could do that. No problem. Cha-cha-cha-cha-cha. All right. Violet says yes. All right, listen. When Violet says yes, I keep moving. All right. Let's see here. Is it just me, Jerry, or do we have a lot of problems in here? I thought I was going to be doing more lecturing. Okay, let's do one more problem, and then maybe Mr. Dion will yak for a little bit. Jeepers, I put a lot of practice problems in here. All right. Yeah, let's try one more. Maybe we're a little practice problem overload here. It says, what amount in moles of each ion is in 35 milliliters of a 0.84 molar solution of zinc chloride? All right. So let's see here. Let's start it with zinc chloride. Could you write out the formula for zinc chloride? Who could tell me? It might not be easy to write it out in the chat or unmute your mic.
It'd be ZnCl2.
Yeah, ZnCl2. Remember, zinc is a transition metal, but zinc only has one possible oxidation state, right, which is +2. And so zinc chloride is ZnCl2. Okay. Before, and you're like, why are you writing solid? If it says right here, it's a solution, right? If it says it's a molar solution. I just want to think of it in terms of ions. You know what? Let's just say it's aqueous, okay? And let's just analyze. We're starting with zinc chloride. That's aqueous. What are the ions? I'm going to have a zinc 2+ ion. How many chloride ions am I going to have? Not a trick question. How many chloride ions would I have? Yeah, exactly. Exactly. I've got 2 here in my formula, so I'm going to have 2 Cl- aqueous. I was talking with my office mate, Dr. Diaz, the other day, and he told me something I hadn't thought of, but he said, look, man, he's like, I've seen students take this, and they'll try to say, I've got 2, I can't even write it, Cl2-, some kind of crap like that. I shouldn't say crap, but anyhow, that's impossible. Okay, there's no such thing. So just try to avoid that. Remember, chlorine is a halogen. They're always going to have a -1 charge, and we've got 2 of them. Okay, so let's analyze it further. Okay, the next thing we're going to need to do is we're going to need to figure out how many moles of zinc chloride we have. Okay, and then we can determine that the ratio of zinc chloride to zinc is 1:1, and the ratio of zinc chloride to chloride is 1:2. Right? And you're like, where did you get those, Mr. Dion? 1, no coefficient. 1, no coefficient. And 2, the number 2 as a coefficient. When there's no coefficient, we assume it's 1. How am I going to get the number of moles of zinc chloride? Well, I've already kind of gone over this with you. So I'm going to say, I take my 0.35 mils of zinc chloride, okay? And I have 1,000 milliliters. I have 1 liter, right? I have to convert this to liters to get the moles, okay? So that's going to cancel out. And then I know I have 0.84 moles of zinc chloride. Oh, not zinc chloride in
I have
1 liter. Just give me 2 shakes of a lamb's tail. So to punch that spinach into my calculator, I end up with 2.9 times 10 to the negative 2 moles of zinc chloride. Go ahead.
Okay, so at the top of the problem, it says 35 milliliters, but you put like 0.35 in the equation. Is you like that?
There we go. I was testing you. There you go. 3.5. All right. So there we go. All right. So we get 2.9 times 10 to the negative 2 moles of zinc chloride. So based off of these ratios that I've written, or this ratio that I've written right here, I'll highlight it again. 1 to 1 to 2. That tells us that if we have 2.9 times 10 to the negative 2 moles of zinc chloride, I must have 2.9 times 10 to the negative 2 moles of zinc ions. And I'm going to have that multiplied by 2 moles of chloride. So I take that number. Oh, did I lose it? I multiply it by 2. I already have it here. I've done it already. And you end up with 5.8 times 10 to the negative 2 moles of chloride ions. So there we go. Now we know how many moles of each ion we have in our solution. Walla walla bing bang. If you're looking for the step-by-step solution, it's written out here, and the check is here and everything, and it even shows you with the dimensional analysis for the number of ions shown right there. All righty. Hey, here's something that doesn't have a problem. I like my thumb up there, just like the chat, you know. This is just dealing with how do you make a solution in the lab if you wanted to dissolve a solid ionic compound in and make a solution of it. In the book, it tells you that you see where this human hand, some person, I was going to say bozo, but that's rude. This person is pouring a solid directly into a volumetric flask. You shouldn't do that, okay? This is a volumetric flask. And the reason why is because you can't heat volumetric flasks. You can't put them on a hot plate. The correct technique for making a solution is that you would take your solid, you'd weigh it out on a balance. That's step 1. Then you take the solid and you put it in a beaker. And then you dissolve it in a small amount of the solvent. So not the entire volume that you need. You put it in a little bit. And the reason why you do it in a beaker is because this is a beaker. And you can heat a beaker. You can take the stirring rod. You can smash it up, right? Whatever you need to do, okay? Once you've got it in solution, then you pour it in, okay? Then you add, I don't know what distilled water is, but distilled water. And you fill up the volumetric flask to the line, right? So the meniscus is just at the line. So you put your eyeball, this is a human eyeball, at the level of the meniscus. So you might have to crouch down. And when it's at that level, I can't read. Can anybody see what the volume of this flask is? Is it a 500? Looks like a 500. So when it's right there, you would read that as 500.00 milliliters. So it's calibrated to the hundredths place. Kind of cool, huh? Then you would stop it and shake. Telling you, I did a chemistry degree, and I obviously had to study analytical chemistry, and I did well in the class, but I wasn't particularly fond of the lab. I didn't really enjoy it a ton. And I remember that I made, just hundreds of solutions, Anyhow, that's how you make a solution. What else can you do? It says here, converting a concentrated solution to a dilute solution. What the heck is going on here? Okay. Here we have a concentrated solution on the left, right? You see you have some particles in there. You see it's got kind of a dark blue color here, And then what happens is you add some more solvent. You're not adding any more particles. You're adding more solvent. And what that does is it's going to make the space between the particles even bigger. You notice that they're closer here, they're tighter. So all you've done is you've diluted or separated the particles more. So it says here in the dilute solution, the same number of solute particles are present in the larger volume. So fewer solute particles are present per unit volume. Keep in mind, remember what I told you that I like to use little n to represent number of moles? Okay? The n here is equal to the n here. You didn't, and you're like, well, there's less particles in that circle. That circle is saying that there's less particles per unit volume. Give me a thumbs. I just want to ask you one quick question. If I called this flask 1 and I called this flask 2, give me a thumbs up if you understand that N1 is equal to N2. The number of moles is not changing. Give me a thumbs up if you understand just that one statement. Number of moles didn't change. Okay, I added more moles of water, but that's not what we're talking about. Water is the solvent. We're talking about the solute. Good. Thanks, Kenner. Thanks, Joshua. Perfect. Okay. Bryn, the whole gang. Okay. Excellent. Matthew, great. Excellent. Okay. So if you understand that, you're going to love my next formula. Because remember that I told you that the number of moles is equal to the molarity, the concentration multiplied by volume. Oh, you wait until we tie this all together. You're going to just jump up for joy. Okay. It says here, preparing a dilute solution from a concentrated solution. This is something that we do all the time in our daily lives. Now, down here in the States, people don't do this as much, but in Canada, everybody has less money because the government takes it all. And the way that people make orange juice in Canada is you always buy it from concentrate in those cans. Does anybody make orange juice from concentrate besides me? Like 99 cents a can. It's a beautiful thing. Okay, Millie. All right, good. Me and Millie and Violet. Okay, we're all into Lindsay. We're into the canned orange juice, right? You take that can and then it says you add a certain amount of water to it, right? It's so much better. And then you make a more dilute and more tasty solution. So look, this is something that is very commonly done in lab. It says here, isotonic saline is a 0.15 molar aqueous solution of sodium chloride. How would you prepare 800 milliliters or 0.8 liters of an isotonic solution or isotonic saline from the 6 molar stock solution? So you remember how you bought the orange juice and it was more concentrated? A stock solution is more concentrated, right? You want to go from this concentration to this concentration, which is lower. What is the formula that we're going to use to do this? Let me show you. We know that in our solution, the number of moles didn't change, right? What did I tell you just a few minutes ago? I said the N1, the initial number of moles, is going to be equal to N2, and I'm going to call that N final. Okay. You could also say the number of moles in the dilute solution is going to be equal to the number of moles in the concentrated solution. The same darn thing. And you guys gave me the thumbs up and you said, look, Mr. Dion, I understand that when you're diluting, you're not changing the number of particles, you're just spreading them out. You're making them more faint. Look, that is why, and I forgot to mention this, that is why when the person diluted the solution, what did the blue color? It became more faint. It doesn't mean that there's less blue particles. They're just more spread out. Okay, so based off of all that spinach that I just said, we can come up with this beautiful formula. Again, since we know that N is equal to M times V, and we know that N initial is equal to N final, we can write M initial times volume initial is going to be equal to M final times volume final. Sometimes you'll see this formula called M1 V1 is equal to M2 V2. It is the formula that you need to solve dilution problems. Let me show you how we do this. We know from the problem that we want to make isotonic saline. So we know that we want our M2, we want it to be 0.15 molar. That's what we want to make. We know that we're starting out with initial volume of V1 of 0.80 liters, and our initial molarity of M1 is what? 6.0 molar. Now look, we're going to use this formula and we're going to solve for what's the volume that we need. You should be able to do this. You should be able to take this formula and say that V2 is going to be equal to M1 times V1 over M2. Like that. Now all we have to do is plug our numbers in. our M1 is 6.0 molar, our V1 is 0.80 liters, and our M2 is 0.15 molar. Well, looky. Molarity cancels out, and I end up with liters. When I punch that spinach into my calculator, and I have my solution on another page, I end up with something. Try not do this one. Good gravy. End up with. Did anybody else solve this one? Let me get my calculator. 6 times divided by 12.5. I made a mistake here.